Somewhere on a mountaintop in Chile, right now, a machine the size of a small house is doing something no instrument built by human beings has ever done before. It is not just taking pictures of the night sky, it is recording the entire southern sky in motion every single night, catching things that move, things that explode, things that appear out of nowhere and vanish just as fast. And in the last few weeks, this machine has started sending back results that scientists are still struggling to fully process. Not because the universe suddenly changed, but because we finally built something powerful enough to see what was always there, hiding in plain sight, in numbers nobody was prepared for. This is the Vera Rubin Observatory, and what it just captured is forcing astronomers to admit something uncomfortable. We have been flying blind. Stay with me, because by the end of this, you are going to look up at the night sky differently. I am your name, and this is your channel. If stories like this are what you come here for, subscribe now, because we are just getting started. Let's start with what this thing actually is, because the scale of it is almost impossible to picture. The Vera Rubin Observatory sits at almost 9,000 feet above sea level on a mountain called Cerro Pachon, in one of the driest, darkest, clearest patches of sky left on planet Earth. At its heart is a mirror over 8 meters wide, one of the largest optical surfaces ever built for astronomy. But the mirror is not even the most insane part. The most insane part is the camera bolted behind it. It is the size of a small car. It weighs about 3,000 kilograms, and it captures images at a resolution of 3.2 billion pixels. To put that into a number your brain can actually hold on to, you would need several hundred ultra-high definition television screens lined up side by side just to display one single photograph this camera takes. One image from this telescope covers a patch of sky 45 times the size of the full moon, and it can do that every 40 seconds, all night, every night, for the next 10 years. This machine went live on July 1st, 2026. Its mission is called the Legacy Survey of Space and Time. And what that means, in plain language, is this. For the next decade, the Rubin Observatory is going to photograph the entire visible southern sky over and over again, roughly once every 3 to 4 nights, building what scientists are calling the greatest cosmic movie ever made. Every star, every galaxy, every faint smear of light that changes brightness or shifts position between one image and the next gets flagged, logged, and cross-checked automatically by machine learning systems built specifically to catch the difference. And this is where the story stops being a nice piece of engineering trivia and starts becoming something much bigger. Because in the first hours, the first weeks, the first few months of this telescope, simply testing its own systems, before the real survey had even formally begun, it had already rewritten the numbers science thought it understood about our own solar system. During its testing phase alone, in roughly 10 hours of observation, Rubin identified over 2,000 previously unknown asteroids. Not 2,000 over a year, 2,000 in 10 hours. 7 of them were near-Earth objects, meaning their orbits bring them into our neighborhood, close enough that astronomers need to track them carefully. Then, as the commissioning period continued over the following months, that number kept climbing. 11,000 new asteroids identified before the survey had even officially started. 33 of those were near-Earth asteroids that nobody on this planet knew existed until this telescope looked in their direction. 380 more were objects orbiting far out beyond Neptune, in the cold outer reaches of the solar system, where almost nothing has ever been mapped. For comparison, every other observatory on Earth and in orbit combined typically finds around 20,000 new asteroids in an entire year. Rubin matched a meaningful fraction of that in a matter of weeks, while it was still being calibrated, before its actual 10-year mission had even begun. Sit with that for a second, because this is the part that should genuinely unsettle you. Every single one of those asteroids has been out there this whole time, silently orbiting the sun, crossing and recrossing paths with the inner solar system, some of them close enough to Earth's orbit to matter, and we had no idea they existed, not because nobody was looking. Astronomers have been scanning the sky for near-Earth objects for decades, but the tools available to them simply were not sensitive enough, fast enough, or wide enough in their field of view to catch objects this faint, this small, or moving this quickly. It took a telescope specifically engineered to hunt down exactly this kind of hidden population, before the true scale of what was quietly circling our solar system became visible. And Rubin's own science team has been explicit about the target. The United States Congress has set an official mandate to identify 90% of all potentially hazardous near-Earth asteroids larger than 140 meters wide, meaning any asteroid big enough to level a city or worse if it ever found its way toward Earth. Before Rubin, filling in that catalog was projected to take decades at the current pace. Scientists working on this mission now believe that with Rubin's survey running at full speed for its planned decade, that 90% target is finally within reach. which means the honest, unglamorous truth behind the word terrifying in this story is not a monster or a doomsday rock on a collision course. It is something quieter, and in some ways more disturbing. It is the sudden, undeniable proof of just how much has been moving through our solar system this entire time, completely undetected, completely uncatalogued, completely unknown to the species living on the one planet all of that debris orbits around. And it is not just the sheer number of asteroids that has scientists paying close attention. It is what Rubin is revealing about how these objects actually behave. In one of the very first peer-reviewed papers to come out of this observatory's early data, astronomers identified the fastest spinning asteroid ever recorded, a rocky body over half a kilometer wide, roughly the length of 8 football fields laid end to end, completing a full rotation once every 2 minutes. Think about the physics of that for a moment. An object with real mass and real gravity, spinning fast enough that if it were held together loosely, the way many asteroids are, by nothing more than gravel and dust clinging together under weak gravity, centrifugal force should be tearing it apart. And yet there it is, intact, spinning through the dark at a speed nothing this large had ever been clocked at before. In that same early batch of observations, Rubin's team identified 19 separate asteroids spinning at extreme record-breaking speeds, each one a body that had been sitting in the catalog of unknowns until a telescope finally had the imaging speed to catch it rotating in real time. Astronomers pulled 76 reliable rotation measurements out of just the earliest, still unprocessed data set, a number that hints at how much routine, previously invisible behavior in our own solar system has simply never been measured before. Every one of these objects has been spinning exactly like this for who knows how long. We just never had a camera fast enough and wide enough to catch it happening. Now let's talk about what happens when this telescope isn't looking for asteroids at all, because that's where things get even stranger. On February 24th, 2026, Rubin ran its very first live test of what is called its alert system, the network built to automatically flag anything in the sky that changes between one image and the next. In a single night, pointed at just one patch of sky that already had enough reference images built up to compare against, Rubin generated 800,000 individual alerts. 800,000 things in the sky that had changed brightness, changed position, appeared or disappeared, all flagged and pushed out to astronomers around the world within about 2 minutes of the image being captured. Supernovae, dying stars, newly discovered asteroids, variable stars pulsing in ways nobody had mapped before, active galactic nuclei flaring with sudden bursts of energy from feeding black holes at the centers of distant galaxies. All of it, all at once, in a single overnight run of a telescope that had not even started its real mission yet. And here's the number that should really stop you. Once the full 10-year survey ramps up to its planned operating speed, Rubin is expected to generate up to 7 million alerts like this every single night. Not per year, per night. Roughly 10 to 20 terabytes of raw data collected in a single evening of observing. More information gathered in Rubin's first year of operation than every other optical observatory on the planet has collected across the entire history of astronomy, combined. Scientists studying supernovae have described this as being able to catch stellar explosions up to 100 times fainter than anything previous surveys could detect, meaning entire categories of cosmic events that were simply invisible to humanity until this year are now going to show up night after night in Rubin's data stream. Astronomers are already talking about candidates for something called a failed supernova, a star so massive that instead of exploding outward in a violent death, it silently collapses inward and effectively vanishes from the universe without the fireworks anyone expected. Finding events like that requires exactly the kind of faint, wide, and fast imaging that Rubin was purpose-built to deliver, and it is finding them within its very first months of operation. But the discovery that connects most directly to the deepest mystery in modern physics is the one Rubin was actually designed around from the very beginning. This telescope is not named after just anyone. It is named after Vera Rubin, an American astronomer who, in the 1970s, discovered something that broke the physics of the time wide open. She was studying how fast galaxies rotate, and she found that stars on the outer edges of galaxies were spinning around their centers far faster than the visible matter. And those galaxies could possibly explain through gravity alone. According to everything known at the time, galaxies spinning that fast should have flown apart. They didn't, which meant something invisible, something with mass but no light, was holding them together. That invisible material became known as dark matter, and more than 50 years later, we still do not know what it actually is. It makes up over 80% of all the matter in the universe, and it remains one of the biggest unanswered questions in all of science. This is the exact mystery the Rubin Observatory was engineered to help solve. By photographing tens of billions of galaxies over 10 years and measuring, with extraordinary precision, how their light bends and distorts as it travels toward us, a phenomenon called gravitational lensing, scientists are hoping to map the invisible scaffolding of dark matter that holds the visible universe together, At the same time, by tracking exploding stars called Type 1a supernovae. Across billions of years of cosmic history, Rubin is also central to the hunt for dark energy, the mysterious force that appears to be causing the expansion of the universe to accelerate rather than slow down. Together, dark matter and dark energy make up roughly 95% of everything that exists. And the honest, almost dizzying truth is that we do not know what either of them actually is. We have spent decades building models around the 5% of the universe we can actually see and touch and measure directly, while the overwhelming majority of reality itself remains completely invisible to us. Rubin is the first instrument built specifically with the raw imaging power and observing time to start mapping that invisible majority directly, rather than inferring it indirectly the way every previous generation of astronomers has had to. And then there's the part of this story that ties directly back into one of the strangest frontiers in modern astronomy, the search for objects that do not belong to our solar system at all. In the entire recorded history of astronomy, humanity has only ever confirmed 3 objects passing through our solar system that originated from somewhere else entirely, out among other stars. The first was an object called Oumuamua, discovered in 2017, a strange elongated body that tumbled through our solar system and left scientists arguing for years about its exact nature. The second was a comet called Borisov, discovered in 2019. The third, discovered far more recently, is an object known as 3I/Atlas, only the third confirmed interstellar visitor ever detected passing through our cosmic neighborhood. 3 objects in the entire history of telescopes pointed at the sky. Rubin's science team has said plainly that this observatory is expected to be the single most effective instrument ever built for catching objects exactly like these, because it can detect faint, fast-moving bodies at a scale and a speed that no previous survey could match. Which means the 3 interstellar visitors humanity has ever confirmed may turn out to be an almost laughably small sample of what is actually passing through our solar system on a regular basis. Material ejected from other star systems entirely, drifting through the space around our own sun, previously invisible to us, simply because we never had a telescope wide-eyed enough and fast enough to catch it happening. There is one more mystery riding on the back of all this data, and it is one astronomers have been chasing for over a decade without an answer. Out beyond Neptune, in the freezing dark of the outer solar system, a strange pattern shows up in the orbits of a small cluster of distant icy bodies. Their paths through space are clustered together in a way that basic physics says should not happen by random chance. For years, the leading explanation has been that something massive out there, an undiscovered 9th planet, several times the size of Earth, is quietly tugging on those orbits with its gravity from some vast, dark, currently unmapped stretch of the outer solar system. Nobody has ever seen it directly. It has never been photographed, never confirmed, existing only as a shadow implied by the way smaller objects around it seem to be nudged out of place. Rubin was built in part specifically to settle this question once and for all. With its ability to catch faint, slow-moving objects far beyond the orbit of Neptune, scientists working on the survey have said plainly that if a 9th planet genuinely exists out there, this is the telescope that is finally going to find it, sometime within the next few years of observing. And even short of that, Rubin has already logged hundreds of new trans-Neptunian objects in its earliest test observations alone, objects drifting through exactly the kind of remote, poorly mapped territory where a hidden planet would need to be hiding. Whatever is out there tugging on those orbits, we are, for the first time in human history, actually pointed at it with an instrument capable of finding the answer. Now step back and put all of this together, because this is where the real weight of the story sits. In less than 1 year of operation, most of it spent in preliminary testing before the real survey had even begun, this single telescope has already uncovered thousands of asteroids nobody knew existed, including dozens close enough to Earth's orbit to matter for planetary defense. It has proven it can generate more scientific alerts in a single night than most observatories generate in months. It is actively hunting for the invisible substance that holds every galaxy in the universe together, a substance we still cannot directly explain more than 50 years after it was first discovered. And it stands positioned to become the most powerful tool humanity has ever had for detecting objects that came from other solar systems entirely, drifting silently past our own sun. This is not a story about aliens or hidden messages or some conspiracy the observatory is covering up. It is something more grounded, and if you actually sit with it, more unsettling in its own way. It is proof, delivered in hard data over just the past several months, that the sky above us has always been far busier, far stranger, and far less understood than we assumed, right up until we finally built something capable enough to actually look. For the next 10 years, this telescope is going to keep doing exactly this, night after night, image after image, cataloging a version of our own cosmic neighborhood that has never been mapped in this kind of detail before. Millions of new asteroids, millions of exploding stars. A working, evolving map of dark matter stretched across the observable universe, and quite possibly more visitors from other solar systems than humanity has ever confirmed in the entire history of looking up. The team behind Rubin has said this is only the beginning, that what has already been found in these first months is, in their own words, just the tip of the iceberg. Which means the real question is not whether Rubin is going to keep finding things that reshape what we think we know. The real question is whether we are ready for how much has genuinely been hiding above us this entire time. If this story pulled you in, subscribe and turn on notifications, because we are going deeper into what this telescope finds next. Drop a comment telling me which part of this surprised you the most, and share this with someone who needs to understand just how much of the universe we are only now starting to actually see.